Lecture 26, Uniprocessor Scheduling. So, as you may imagine, processor scheduling can be a lot more complex when we have multiple threads and multiple processors, so we'll start with a simpler version, the Uniprocessor Scheduling 1 CPU, and then build on that a little bit later on to look at multiprocessor scheduling. So, yeah, there are only 4 rules. Make the plan, execute the plan, expect the plan to go off the rails, and throw away the plan. It's going to be complicated, but it'll be okay. Scheduling is relatively easy to define as far as we are concerned. It is given that we have multiple threads in the system, we have to make some decisions about when they get to execute. Okay, well that's easy. Of course, the devil is in the details. There's 4 types of scheduling. The last one that's listed there, I/O scheduling, is for later. It has its own topic when we talk about I/O devices, but the other 3 bear at least a little bit of examination right now. So long-term, medium-term, and short-term scheduling are the things that we will be discussing. Today we will discuss actually all 3 of those, but most of the focus goes on item 3, the short-term scheduling. Let me give you a student-relevant analogy to explain the different levels. Long-term scheduling is about deciding what courses you want to take in your degree. So you have a complementary studies elective, a non-technical elective, and you say, all right, I want to at some point take Econ 102. Right? This is a non-technical elective. You haven't decided exactly when and how it's all going to work, but this is something you would at some point like to take. Medium-term scheduling is about deciding what courses you want to take in a given term. So you're going to enroll in your 4A term, and you're going to say, all right, am I going to enroll in Econ 102 this term, this 4A term, or am I going to defer it and take it in 4B? And then there is short-term scheduling. And short-term scheduling is deciding what you're going to do right now. Like, I'm going to study SE 350 because the final exam is tomorrow. That's what I want to do right now. I don't care about the someday, and it doesn't matter what other courses I'm enrolled in this term. I'm making just a decision about what to do right now. So the long-term scheduler, if you will, is responsible for determining what programs are going to run at all. In a system that has limited maximum concurrency, it's about deciding how many things we allow concurrently, what we're going to do. And it controls, if you think back to the process state diagram, a transition from the new state to the ready state. And once it gets into the ready state, then it's in the purview of a medium or short-term scheduler. This is not something we do a lot in desktop or laptop systems. Your common operating system these days, it puts it in the hands of the user which programs are open. Right? You decide, I want to start Chrome and Firefox and Safari and 10 other programs, and you can do it. Right? The user chooses what to do, and it's not typically an operating system decision. Sometimes it is in a batch processing system, like when one task terminates, then the operating system might be responsible for starting another one, and it'll choose somehow which one it's going to select as the next one. But your desktop or laptop, or even to some extent phone operating system, lets you open as many things as you want to open. So there are sometimes limits, right? You might have like a maximum of, say, 100 processes on your system. If it's an ECE Ubuntu server or whatever, we set a limit of how many processes an individual user can have, because it just prevents, shall we say, anyone from accidentally or otherwise monopolizing resources that they shouldn't monopolize. But typically, your operating system doesn't stop you and complain. Now, we do sometimes encounter in real life long-term scheduling, right? Usually it's a remote service that is deciding to manage its resources. If you're trying to log into a game on launch day, for an online game, you may receive an error saying that the server is busy/full. This is the server telling you that it will not start a new game for you. That is to say, it won't launch a new process because it has reached a limit of how many processes games are currently permitted. Only when some people log out and some games terminate will it be permissible to create some new ones. I used to reference here my experience with the game Diablo 3 on launch. That's something like 8.5 years ago at the time of recording. So I think it's far enough in the past that it's no longer relevant. I don't think anybody remembers it, but that's fine. It's maybe no longer relatable. But probably there are other games that are like this as well, that when you try to log into something on launch day or when a new expansion is released or something like that, you end up getting a bunch of error messages that say, no, sorry, not allowed, because some limit has been reached. That's most likely your most common experience with long-term scheduling. Mobile operating systems like Android can be a bit more aggressive about telling you they reach their limits than desktop ones. If memory is running low, Android can and will kill and suspend processes to make room for new ones. Then there's medium-term scheduling. And medium-term scheduling is a little bit more interesting than long-term scheduling, if you ask me, and it revolves around this idea of swapping processes into memory and to disk. A process that's swapped to disk completely is not going to run in the immediate future, but is likely to run before some period of time has passed. So swapping a process to disk takes it out of the realm of the short-term scheduler, and returning it to memory puts it back in the realm of the short-term. But the medium-term scheduler doesn't really serve as much of a purpose as it used to because, well, disk transfer times are not as painful as they were when there were magnetic drives. And, I mean, it's not more interesting, really, to talk about than short-term scheduling. Because short-term scheduling is actually the focus. It's where the real action is. It's where we're realistically going to spend the remainder of our time talking about scheduling. And short-term scheduling is also sometimes called the dispatcher, and it's not about someday and sometime and whatever. It is what we're going to do right now. And the short-term scheduler is going to be invoked by the operating system a very large number of times. Anytime something gets blocked, anytime a time slice is expired, anytime we need something to do, we're going to invoke the short-term scheduler. So it's very important we have to do a good job, right? Just choosing randomly or whatever might be simple to implement, but it's going to cause quite a headache. So there is going to be a need for the short-term scheduler in a few different situations, and I mentioned a couple already, but let's talk about them in some more detail. One of them is cooperative multitasking. And short-term scheduling will happen in a cooperative multitasking system where a currently executing thread voluntarily yields the CPU, or it terminates, whether it terminates voluntarily or with an error. Some ancient operating systems, and Mac OS, the classic one, was like this. It required processes to have a yield call to make the best use of the CPU. This feels a little bit insane in the modern day, but there do exist things like a pthread yield call where you can specifically request that I would like to let another thread proceed. That's not how most operating systems work these days. This is pretty far back in the Pepperidge Farm Remembers kinds of history, but they did at one time work at least some of the time like this. Okay. For reasons that are presumably obvious, hint, some people are jerks, cooperative multitasking is a little bit problematic, and what we're actually going to talk about is preemptive multitasking, and that is the operating system, not the running process, is responsible for making a decision about when it's time for a switch. Look at me, I'm the captain now. We no longer get to choose entirely. As I said, something like pthread yield does exist, so you can volunteer yourself, but the operating system is going to be the one that makes the call most of the time. So some of the things still carry over. I mentioned yield, and in preemptive system, processes still terminate, and they still get blocked, and all of those are still occasions to run the short-term scheduler. There's lots of things that can cause our thread to get blocked. It's not a mystery to us at this point because we've covered that, I would say, in in extensive detail at this stage. When there's an I/O operation, maybe it's we're blocked on network, maybe it's something else. If there's a mutex, if there's a page fault, all these things are not new to us, and you can probably think of some more that don't appear on the list as causes for why our currently executing process might be blocked temporarily, waiting for something else. So that's when we're going to find something to do. And I mentioned this quite some time ago in the notes and in the videos, which is that after we handle an interrupt, that's also potentially an opportunity to change what task we're working on. After the interrupt is handled, we can return to execution just where we were, or we can pick up something else and carry on from there. There's no rule that says you have to do one or the other, right? The original process is already suspended. You could, if you wanted, leave it in that state and move on to something else. Now, a system call like fork or even signaling on a semaphore is also, again, an opportunity to switch from one process to another, because when we invoke the system call, we call the operating system, the caller is suspended, and it's necessary then to decide what process is going to execute next. And when we talked about fork from the calling perspective, there was a lot of emphasis given over to the idea that, like, we don't know whether the parent process or the child process is going to be the one that continues executing first, or maybe they execute concurrently after the call to fork. And we said, well, it's the operating system's decision and we can't really influence that. Well, now we're the operating system, so now we do get to implement this, right? And there are a couple of criteria, right? Priority might be one of those things. And choosing whether the parent or the child runs first may be a question of priority, or it might just be sort of random luck because they're equal in every regard, so we just choose one. It's not easy to say, so we don't know 100%, but we'll make our best decision using the criteria that we have. Right. Similarly, we also acknowledged this when we said, okay, if we signal on a semaphore or post on a semaphore, we're not entirely sure which of the processes that's waiting will be the one to receive the signal. And even then, of the two, the one that called the signal and the one that received the signal, which of those will be the one to proceed? We said we don't know. We said that's the operating system's decision, and it's difficult for us to have influence over it. But yeah, from the point of view of the operating system, it will decide based on whatever scheduling algorithm it has decided to implement and whatever criteria the scheduling algorithm that is implemented uses. Finally, there is also time slicing. And this is another occasion that causes a process switch. And this is about dividing up the available CPU time amongst the various CPUs. This is a preemptive part of preemptive multitasking, which is that your program may execute for some period of time, and when time's up, there is a process switch, and another one gets an opportunity to run. If time slices are defined as T time units, the implementation looks like, well, every T time units, there's a clock interrupt that's generated. When we handle this interrupt, the process for handling it is running the short-term scheduler to choose what process runs next, and so it makes it seem like different processes run concurrently. Obviously, if we don't do this, there could be a couple of bad things that happen. What we would really like to avoid is a potential for one process to get too much CPU time if we don't do this. Okay, we'll also talk about process behavior. And it's noteworthy that processes tend to alternate periods of, shall we say, computing, like using CPU time, with input and output requests. And these really do tend to alternate according to what we see. A typical program that exhibits this kind of behavior, loads some data, processes it, goes to the next chunk of data, loads it, processes it, and so on and so on. And that's just how the program executes. So during the period of time when the CPU does a lot of work, we call that the CPU burst. And then there's the I/O, and there's a period of waiting for the I/O, which we call I/O burst. So not every thread follows this alternation pattern, and the time spent on each is very rarely 50-50, but nevertheless, we do see there are patterns, and we do see there is a spectrum, right? There are programs that just do I/O stuff. They hardly do any computation, so all of their time is I/O burst. And then there are programs that do very little to no I/O, and they spend all their time using the CPU, so they have a lot of CPU burst. It's not really, a clear line between one and the other. You can think of it as a spectrum, and where they fall on the spectrum probably allows at least some degree of classification. So processes that spend, we'll say, most of their time computing are CPU bound. That is to say, the limiting factor in their execution is how fast the CPU can execute the code. The alternative are processes that spend much more of their time waiting for I/O, and we would describe them as being I/O bound. In this case, having a faster CPU will not make the difference. And you'll notice I use sort of the definite article in that, make the difference, because having a faster CPU does help programs that are I/O bound, right? They do still use CPU time, and so in principle, getting a faster CPU would result in faster execution of the I/O bound process, but not very much, right? If the process is CPU bound, increasing the speed of the CPU might result in a meaningful improvement of the execution time. If we do it on something that is I/O bound, maybe we get 1% improvement or 0.5% improvement. It's not nothing, but it's not the end of the world. It's if we don't have it, right? So if you wanted a visual representation here in sort of a diagram, then the gray boxes represent CPU burst, and then the black lines represent waiting for I/O. And more or less, a CPU-bound program looks like A. There's a lot of CPU time with some I/O stuff in between, whereas an I/O-bound program looks like B in the diagram, where the CPU time is pretty small, and a lot more of the time is going towards the I/O stuff. So studies have been done on this, but over time we find that CPUs get faster at a rate much higher than the rate of I/O speed up. Right? This is probably not surprising to you. A new CPU comes out every few months, and the one you can get today is measurably better in terms of benchmarks as compared to a CPU from 6 months ago. But the same can't really be said about the I/O devices. I/O standards like serial ATA and USB and what have you change very slowly over the course of years. Just take a scan over this and tell me how many of these connectors do you recognize, and how many of them have you used? Right. Here's a picture from the back of a motherboard. It represents a lot of different connectors, and over time a lot of them have migrated, if you will, to USB. So you would probably in the future not see some of these ports, and you would see some additional USB. But what would you see, right? I mean, some of them are so ancient as to be retired at this point. The one labeled 3, the parallel port, used to be used for printers, but we don't do that anymore. Printers are USB or network, or you print at the Davis Center, because why should you own a printer? But these things sort of do exist, right? So over time, it does make some amount of sense that we end up trending towards programs being I/O bound, right? When there is a jump forward in device speed, like USB 2 to USB 3, it tends to be a pretty large jump, and it's pretty dramatic, but then it plateaus for a long time. So over time, programs tend towards being I/O bound. And the results of the study look something like this, that a great amount of the CPU bursts are very short, like less than 4 milliseconds, and then there's a significant chunk between 4 and 8, and there's very small numbers beyond that of CPU burst frequency. Hey, this graph actually has some numbers on it. We'll take it. So what does this have to do with scheduling? Why do we care about CPU burst and I/O burst? In some systems, an I/O and CPU balance would help us to make the best use of the resources, right? If the long-term scheduler is trying to keep an eye on like how much is the CPU being used versus how much are the I/O devices being used, it could potentially make some decisions that help with making best use of both of these resources, right? It does require the long-term scheduler to have some idea about which processes are which, but observing the behavior of processes is usually enough to give us a pretty good hint as to what is actually going on. Now, another thing is that if disk is slow, one of the things that we could do that would maximize the performance of the program would be to try as hard as we can to keep it busy at all times. And then that would look like, effectively, if the disk is not busy, there's no tasks waiting for the disk, is to immediately schedule a process that's likely to issue a disk request, because our goal, as I say, is to keep it busy at all times.